Hello, today we're going to be talking about operations with radicals. Our objectives for today are that students will be able to simplify radical expressions, and students will be able to add, subtract, multiply, and divide radical expressions. Let's get started. Alright, the first operations with radicals that we're going to talk about is adding and subtracting radicals. So the first thing you want to do is simplify all of your radicals completely. Then you want to identify the radicals with the same index. So look for ones that are square roots, look for ones that are cube roots. And they have to have the same radicand. So they have to have the same number inside the radical. Only these can be combined. So they have to have the same index and the same radicand. They're the same square root, so they're square roots, cube roots, fourth roots, and they have the same number inside. For common radicals, add and subtract the coefficients, so whatever's on the outside, and keep the common radical. Let's do a couple examples. All right, the first thing we want to do is simplify these radicals. So what we want to do is break down square root of 27, and we want factors that are perfect squares. So 9 times 3. Rad 9 times rad 3 gives us rad 27. We can break down square root of 12. Rad 4 times rad 3 because 4 is a perfect square. Then take the square root of 9. Don't forget to bring down that 3. So 3 times square root of 9 gives us 3. And then bring down the rad 3 because we can't simplify that any further. Minus 2, don't forget to bring down that minus 2. Times the square root of 4, which is 2, times rad 3. Bring it down because we can't simplify it any further. 3 times 3 gives us 9 rad 3 minus 4 rad 3 because 2 times 2 gives us 4. Then we see that they have the same index. They're both square roots. They have the same number inside, or they have the same radicand. So then we can take the coefficients, 9 and negative 4, right? We can do 9 minus 4 gives us 5, and we keep the same radicand. We keep the same square root. So our final answer is 5 rad 3. All right, number 3. We first want to start by simplifying all of our radicals. So start with the fourth root of 48. Look for factors of 48 that are perfect fourths. So 1 times 48, none of them are perfect fourths. 2 times 24, nope. 3 times 16, yes, 16 is a perfect fourth. We know 2 to the 4th power gives us 16. So those are the factors that we want to use to break down the fourth root of 48. So break it down to the fourth root of 16 times the fourth root of 3. Don't forget to bring down that 7. Then rewrite this. We can't simplify that any further, so minus 2 times the fourth root of 3. Then we want to try to break down the third root of 72. So look for factors of 72 that are perfect cubes. 1 times 72. 2 times 36. 36 is a perfect square, but not a perfect cube. 3 times 24. Nope. Let's see, does 4 go into it? I believe so. 72 divided by 4. Yep, 18. Not perfect cubes. 5, nope. 72 divided by 6 gives us 12. Still not perfect cubes. 72 divided by 7. Nope, that's a decimal. 72 divided by 8 gives us 9. And 8 is a perfect cube, so there's our factors we want to use. So we break that down to be the cube root of 8 times the cube root of 9. And don't forget to bring down the plus 3. All right, then we want to simplify what we can. So the fourth root of 16 gives us 2. So we've got 7 times 2 times the fourth root of 3 minus 2 times the fourth root of 3 plus 3 times the cube root of 8 gives us 2 times the cube root of 9. Then we want to simplify even further. 7 times 2 gives us 14 times the fourth root of 3 minus 2 times the fourth root of 3 plus 3 times 2 gives us 6 times the third root of 9. Then we see that this one and this one have the same, they have radicals with the same index and the same radicand, fourth root of 3, fourth root of 3, so we can combine the coefficients. So 14 minus 2 gives us 12, and we leave our fourth root exactly the same. All right, we keep the common radical, and then bring down the plus 6 third root of 9 because we can't simplify that any further. Now, our two radicals do not have the same index. This is a third root, a fourth root, do not have the same radicand, so we cannot combine them. They are not common radicals. So this would be our final answer. We've simplified it as much as we could, and we are done. All right, number 5. We want to first look at our radical. We've got square root of 98 x to the fourth y squared, and we want to simplify this as much as we can. So we want to look for factors of 98 that are perfect squares. 1 times 98, 2 times 49. 49 is a perfect square, so there's our factors that we want. Break it down into what we can take the square root of times what we can't take the square root of. We can take the square root of 49, can't take the square root of 2. X to the fourth, 4 is a multiple of 2, so we can take the square root of it. Y to the second, 2 is a multiple of 2, so we can take the square root of it. Then we want to be sure to bring down our other side. Don't forget to bring it down. So 3x squared, y, rad 2. Then take the square root of what you can take the square root of. So square root of 49 gives us 7. Square root of x to the fourth, 4 divided by 2 gives us x squared. Y squared, take the square root of that. 2 divided by 2 gives us y to the first power, or 1. 1y. Then we can't simplify this any further, so we bring down the rad 2. Minus 3x squared y rad 2. Now, our coefficients, or what's in front of our radical, have the same variables. They are common or like terms. So we can do 7x squared y minus 3x squared y, and we get 4x squared y. They have the same number of x's, same number of y's, so we can just do 7 minus 3. And don't forget to put the x squared y after it. And we can do this because our radicals are the same. They have the same index and the same radicand. And then we just need to be sure to keep the common radical. And this is our final answer. All right, moving on to multiplying radicals. So when we're multiplying radicals, what we want to do is multiply the coefficients first, and then use the product rule. So the nth root of a times the nth root of b is equal to the nth root of a times b. So we can take our radicand times our radicand and put it under one radical sign. Then we want to simplify the resulting radical. So number 7, square root of 27 times square root of 5. We take the radicand times the radicand, 27 times 5. Put it under one radical sign. 27 times 5 gives us 135. Then we want to look for factors of 135 that are perfect squares, so we can simplify it. 135, we've got 1 times 135. 2 doesn't go into it. 3 times, 135 divided by 3. 3 times 45, not perfect squares. 4, don't believe that goes into it. Nope. 135 divided by 5 gives us 27. 27 is a perfect cube, but not a perfect square. C6, don't think that goes into it. Nope. 7. Let's see. Nope. 8. Nope. Let's see. 8. Nope. 135 divided by 9. 9 over 15. Or 9 times 15. 9 is a perfect square, so there's our winning factors. Break down the square root of 135 to the square root of 9 times the square root of 15. Take the square root of 9, gives us 3. Bring down rad 15, or square root of 15, and there's our final answer. All right, number 9. First thing you want to do is multiply the coefficients together. So 2 times 5 is going to give you 10. Then we see that our radicals have the same index. They're both cube roots, so we can multiply the radicands together. 9 times negative 24 is going to give us the cube root of negative 216. Now we know we can take the cube root of 216, and because it's negative, we're going to end up with negative 6, because negative 6 cubed gives us negative 216. Bring down this 10, so it's 10 times negative 6. And our final answer is negative 60, and we are done. All right, 13. We've got a cube root times a cube root. They have the same index, so we can combine what's on the inside. We can combine our radicands together. So what we want to do is we want to take the cube root of negative 3 times 36 is going to give us negative 108. Multiply the numbers together first. Those are our like terms. A to the 7th, A to the 6th gives us A to the 13th. We add the exponents together. B to the 4th, B squared gives us B to the 6th. Add the exponents together. Then we want to simplify this as much as we can, so we want to look for factors of 108 that are perfect cubes. So 108, 1 times 108, not a perfect cube. 2 times 54, not perfect cubes. 3 times 36, 36 is a perfect square, but not a perfect cube. 4 times 27, let's see, 27 is a perfect cube. So there's our winning factors. We want to break this up into what we can take the cube root of times what we can't take the cube root of. We can take the cube root of negative 27. We always want to get rid of that negative when we can. Can't take the cube root of 4. Then we've got A to the 13th. 13 is not a multiple of 3, but 12 is. So we write A to the 12 under what we can take the cube root of, and we've got 1A left over. And then 6 is a multiple of 3, so we write it under the one we can take the cube root of. Then, take the cube root. So the cube root of negative 27 gives us negative 3. 12 divided by 3 gives us A to the 4th. 3 divided by 3 gives us a single B. And then we rewrite this because we can't simplify it any further, so we're left with cube root of 4A. And this is our final answer because it's as simple as it gets. All right, now let's do a couple of examples when we've got binomials. So binomial is two terms separated by a plus or minus sign. All right, so this right here would be our binomial, and we're multiplying a radical times a binomial. Just like when we're dealing with algebraic expressions, if you've got parentheses and a binomial inside the parentheses, you must distribute what's on the outside. So we have to use the distributive property. We take rad 10, multiply it, times both terms inside the parentheses, multiply the binomial by square root of 10. So square root of 10 times 5 rad 5 gives us 5 times, we do our radicands, multiply our radicands, 5 times the square root of 50. Then square root of 10 times negative 2 rad 2, we get negative 2 because that's our coefficients. 10 times 2 gives us 20. Now, what we need to do is break down our radicals and simplify them before we try to subtract. So we want to break down square root of 50. Right off the bat, we know 25 times 2. We know 25 is a perfect square. And 20, we can break that down to 4 times 5. Then we want to rewrite our terms. So we write a 5 in front times square root of 25, or 5, times rad 2 minus 2 times the square root of 4 is 2 times rad 5. Then we multiply 25 times, or 5 times 5 gives us 25 rad 2 minus 4 rad 5. And we cannot combine these terms because they do not have the same radicand. We can't, even though we've got coefficients in front, it's not the same radicand. Rad 2 is not the same as rad 5. So they are not like terms and we cannot combine them. We cannot subtract. So we are done, and this is our final answer. It has to be as simplified as possible, so that's why we had to break it down. All right, 17. We have a binomial times a binomial. So anytime we have a binomial times a binomial, we have to FOIL. So we want to do 6 rad 6 times rad 6. We get 6 times square root of 36. 6 rad 6 times rad 2 plus 6 times rad 12. Then negative 6 rad 2 times rad 6, so minus 6 rad 12. Then we multiply the last terms together, and we get negative 6 times rad 4. Then we see that positive 6 rad 12 minus 6 rad 12, these are going to cancel out. So we're left with 6 times the square root of 36 minus 6 times the square root of 4. We can take the square root of 36, so we get 6 times 6 minus 6 times the square root of 4 gives us 2. 36 minus 12, and our final answer is 24. All right, 19. We've got an example where it's a single term. We've got a radical times a binomial, so we have to distribute to both terms. So square root of 3k times the square root of 12k. Multiply our numbers together, so 3 times 12 gives us 36. K times k gives us k squared. Then square root of 3k times negative 2 square root 15k squared. So minus 2 times the square root of 3 times 15 gives us 45. K times k squared gives us k to the third. Then we want to take the square root of what we can take the square root of. So we can take the square root of 36k squared. We get 6 and k, because k squared, 2 divided by 2 gives us 1. Then minus 2, we want to try to break down this square root of 45k to the third into what we can factor and what we can't. So what we can factor times what we can't. Right off the bat, we know 9 and 5 are factors of 45, and 9 is a perfect square. So 9 and 5. K to the third, 3 is not a multiple of 2, but 2 is. So k squared goes under what we can factor. We've got 1k left over. Then we want to rewrite it as 6k minus 2. Take the square root of this, so times 3k. Can't simplify this any further, so rewrite it as 5k, or square root of 5k. All right, then simplify what you can. So we've got 6k minus 6k rad 5k. And we can't simplify that any further. We can't subtract. We can't combine any like terms. So we are done, and this is our final answer. All right, now dividing radicals. First thing we want to do when we're dividing radicals is to divide the coefficients. Then you want to use the quotient rule to help you divide the radicals. So the quotient rule tells us that the nth root of a divided by the nth root of b is equal to the nth root of a over b. We can write it under one radical symbol. Then you want to simplify the resulting radical. So, for example number 1, first thing you want to do is divide the coefficients. So 12 divided by 2 gives us 6. Then we want to rewrite the square root of 160 divided by the square root of 5 under one radical. So we rewrite it as square root of 160 divided by 5. Then we know we can divide 160 by 5. So we end up with 6 times 160 divided by 5 gives us 32. Then we want to simplify this as much as we can. So we want to think of factors of 32 that are perfect squares. We've got 16 times 2. Bring down the 6, so we've got 6 times square root of 16 is 4 times rad 2. And then rewrite this as our final answer, 24 rad 2. Alright, last but not least, we're going to talk about dividing radicals and what we do, what happens when we have a radical in the denominator. Alright, so the process for what we do when we have a radical in the denominator is called rationalizing the denominator. So here is number 9. This is an example where we have a monomial in our denominator. And in order to get rid of the radical from the denominator when it's a monomial, what we would need to do is multiply the top and the bottom by that radical. So for this one, what we would need to do is multiply the top and the bottom by the square root of 5. Essentially, we're just multiplying it by a different form of 1 because square root of 5 over square root of 5 equals 1, and we could multiply anything by 1. So then we would just multiply straight across, and we get 3 times rad 5 over 2 times the square root of 25 because we multiply the radicands together. Then we want to simplify this. So we can simplify, we would leave the top as it is, and then we can simplify the square root of 25 to be 5. Then we can multiply the denominator together, 2 and 5, so we end up with 3 rad 5 over 10. And that would be your final answer. Alright, and then the other type of example where we have a binomial in the denominator and we want to rationalize the denominator, what we need to do is multiply by the complex conjugate. Alright, so we've heard those words before, we've seen this concept before. So what you would need to do is multiply the top and the bottom by 4 minus rad 2. So we multiply both the numerator and the denominator by the complex conjugate. Then on top, what we want to do is we need to distribute the 4 to both the 4 and the rad 2. So on top, we end up with, 16 minus 4 rad 2. And on the bottom, we want to FOIL these together. So 4 times 4 gives us 16. 4 times negative rad 2 gives us negative 4 rad 2. Rad 2 times positive 4 gives us plus 4 rad 2. And then rad 2 times negative rad 2 gives us negative square root of 4. Alright, then we want to simplify as much as we can. So in our denominator, these will cancel out. So we end up with 16 minus 4 rad 2 on top. And then here we've got 16 minus the square root of 4, which is 2. We simplify, we subtract 16 and 2, so we end up with 16 minus 4 rad 2 over 14. And then we can simplify further. We can divide each of these terms by 2. So all of the coefficients we can divide by 2 in order to simplify this further. So we end up with 8 minus 2 rad 2 over 7. And that is how we rationalize the denominator when we have a binomial in the denominator. Alright, if you printed out the notes packet, you'll see that there's a lot more problems in this section. They're all very similar. So number 9 and number 15 are the main ideas. These video notes are already long enough, so I don't want to go over too many more examples, but if you want to try any of the odds and if you have any questions on them, please feel free to call me over so I can help you. All right, otherwise, I hope you learned a thing or two about operations with radicals today. Look to the board to see what to do next, and I hope that you have a great day. Bye.